Welcome back, everybody. We're continuing our Chapter 2 notes on kinematics, and this is what you would probably call Section 3. It's a short little section. It's on instantaneous velocity, and up to this point we've been talking about, in Section 1 and Section 2, what distance is and what displacement is, and the fact that that velocity is a certain displacement over time. And one thing that we talked about with velocity was average velocity. Now this is right here is the first slide of instantaneous velocity, or Section 3. But I'm going to go back to a slide that we had before in the previous section that looks like this right here. And it even has my writing still on it right here. Okay? If we have something that has this path, takes this path, it goes in the positive x direction and then kind of stops and goes in the negative x direction, that's the actual path that it takes. All right, it's not. It's going kind of forward and then backwards, you might say. But if we were to take 2 points, point A and point B, and just draw a straight line between them, that would represent the average velocity between those 2 points. In truth, this object is moving very fast in this direction and then kind of changing direction and coming back, but on average you could say it's going at a constant rate between A and B, just like that. All right, you might say the secant line between any 2 points on a position versus time graph would be the average velocity. All right, well, since this section that we're in is on instantaneous velocity, well then how is that different? How is the average velocity different from the instantaneous velocity? Well, the instantaneous velocity, what that does is that tells you at any one point in that path what is the actual velocity that the object has. And I'm going to go move forward a little bit right here to this next slide, and this just might make a little bit more sense. So again, here's a position versus time graph. All right, so this blue line represents kind of the direction that the object is going. Over as time progresses towards the right, this thing moves in the positive direction and then kind of stalls a little bit and really doesn't do much. Maybe even goes backwards a little bit and then moves slightly in the positive some more. Okay, and if you take any 2 points, like between 0 and say here, these 2 points, the secant line between those points would represent the average velocity. This thing moves very fast in the positive direction and then kind of slows down and then just sort of maybe even comes backwards a little bit to right here, but this represents the average. But as we get closer, this and then this secant is a shorter secant. And then this secant is an even shorter secant. And this one here as well. As we get closer and closer together, these 2 endpoints wind up getting closer and closer together. And that's really what the previous slide is. All right? As the change in time approaches 0, that's what this limit says right here. Like, for example, this and this is a pretty significant change in time. All right? Between that and that is a pretty significant change in time. But as you get closer together, it gets less and less. And at some point, the 2 endpoints of the line come together and converge on one single point right there on that line. And that is that line right there, the line that represents that slope. If there were 2 points that are just barely some distance apart, the slope between those 2 points would be the velocity that object has at that point right there. If you can imagine those 2 points becoming one single point, you can't really have a slope of 1 point, but what you can have is you can have a tangent line, and that's what this is right here. This goes from being the slopes between 2 points to being closer and closer and closer together to being a tangent line, and right there, right at that point, the object is tangent to the path. And so at that point, whatever that tangent slope happens to be, I'll draw it as a red line coming off like that. Whatever that slope is at that single point right there, that would be the instantaneous velocity. Now we call that instantaneous because 1 instant later, it's going to be a slightly different slope. Now I kind of exaggerated that, but you can see that as time is going to progress, the slope is going to kind of become less positive and more flat, maybe even negative here a little bit. So in the next instant in time, if you can think of that, if you can picture that next instant of time, whatever that instant of time is, it's going to be a slightly different slope. So different velocity. So instantaneous velocity is really, at any one point, the change in a position over change in time, kind of like the rise over the run, right? But there really is no run because it's not a change in time, it's simply a single point in time. That's what we call the instantaneous velocity. So that's the tangent line at that point in the curve right there. By the way, one thing that you can do to measure your instantaneous velocity, or probably more accurately your instantaneous speed, is to look at your speedometer. It's an instrument that is very good at telling you what your speed is at any one point in time. Even though over a trip, you may be, over a whole trip, you may be going forward and then slowing down and then forward again. At any one point, it gives you your instantaneous velocity, or I should say instantaneous speed. So this brings us to section 4 of chapter 2, and this is a very big concept. This is the concept of acceleration. All right? You know that the velocity and speed are both measures of what distance you cover or what displacement you cover in a certain amount of time. But then what is acceleration? I think most people know that acceleration has something to do with motion. Well, in the same way that velocity can be said to be a change in displacement over time, what acceleration is, it's a change in velocity. Change in velocity over time. My dogs are barking outside. Can you hear them? This is a change in velocity over time. So velocity changes. You know, if you get in your car, you don't drive at exactly the same speed all the time, or there's exactly the same velocity. No, you start from rest and then you get up to speed. What you're doing to get up to speed is you're actually accelerating. You're going faster and faster, you might say in layman's terms. So this is really the average velocity, the average acceleration. So over a certain point in time, whatever your change in velocity is, that would be your average acceleration at any one point in time. We can find instantaneous acceleration by doing the same thing, by taking 2 points and 2 points on a graph. So we'll say we have, I don't know, acceleration graph, kind of like that. All right, and we've got a point in time here and maybe a point in time here, and so that's a delta t. And so whatever the straight line, that's not a very straight line, is it? Imagine that's a straight line. If that were a straight line between those 2 points right there, and the blue line were more curved, then that would represent the slope or the change in velocity over that change in time. In our class, we're going to mainly focus on constant acceleration. So an acceleration at any one point in time is pretty much going to be the average acceleration at any one point in time. Let me put it this way. Let me draw another little graph right here. All right, so that's velocity on the y, and that's time on the x right there. Okay. Yes. So we're just going to have constant accelerations in our class. All right. So is there any change in velocity? I'm sorry. That is wrong. I need to draw it like this. How about like, there we go. Okay. Is there any change in velocity over time? Yeah, you can say that, all right, well, between these 2 points right here, here and here, we've got a change in time, and there's also a corresponding change in velocity as well, and that would give us some acceleration. But what's true about this is the fact that this the slope right here is the same all along this line. This line is not curving back and forth. Basically what we're saying here is that the acceleration, I should make that red, the acceleration is constant. And that's mostly going to be true in our class. You might say average acceleration is going to be the acceleration at any one point in time. All right, so whatever the slope is here, it's pretty much going to be the slope all the way up. Okay? But let's just say, for example, just for the sake of argument, that we do have a changing acceleration, an acceleration that is not constant. All right, this would be a a velocity versus time graph. There's your velocity on the time on the x, and there's your velocity on the y right here. And let's just say that we have a change in velocity over time, like that. Okay. So if we were to get the average acceleration, then the average acceleration would be the secant line between, say, that point and that point right there. Okay? And so if you wanted to find the acceleration, you might say the instantaneous acceleration at any one point in time. This would be the average acceleration. The instantaneous acceleration, then that would be the tangent line at any one point in time. Okay, the tangent there, the tangent here, etc. At any one point in time, that would be the tangent. Now, in order to do that, you need a little bit more advanced math, but we're actually sort of scratching the surface of calculus right here, but I want to be careful about talking too much about that. We're going to focus mainly on constant accelerations, and so if the object has a constant acceleration, this velocity versus time graph is going to have a change in velocity over change in time that is constant. All right, well, not a very straight line right there. Let's try that again. Constant line like that, all right? Still not the greatest, but you get the idea. So the average acceleration between this point and the instantaneous accelerations all along here, you might say that secant line and the tangent lines are all the same thing when you have a constant acceleration. All right, so that's what's going to make our class a little bit easier conceptually. I did a couple little sketch drawings right here, but this might make it a little bit clearer. All right, so if you have velocity versus time, you've got a changing acceleration. You're accelerating positively and then negatively and then coming back up again. All right, here are the secant lines, here and here. All right, and they tell you the average acceleration between T1 and T2 and T2 and T3. But at any one point in time, the tangent line would be the instantaneous acceleration. This happens to be the instantaneous acceleration right at time 3 right here because it is tangent to that green curve right at time 3. So when people think of acceleration, most times they think of going faster. And that is changing your velocity, increasing your velocity, all right? But we can also have deceleration, and deceleration is a slowing down, you might say. You know, when you come to a stop sign, your brakes help decelerate your car. A deceleration is just as much an acceleration as an acceleration is, all right? It's simply a change in velocity. Now, it just happens to be a negative change in velocity over time, but you're slowing down. All right, so let me clarify this here for us. When we say that deceleration happens when an object's velocity and acceleration have opposite signs. Okay, well, what happens if you take just take a ball, all right, and you throw it up in the air? Now, it's moving upwards, okay? So the velocity, we'll call that positive, okay? But is it going to keep moving up positively? I mean, it's got a positive velocity. Well, it's not going to keep moving up positively because something is acting against it. There is an acceleration that we call gravity that is acting in the opposite direction. I'm going to call that a G right there. And we'll get into that in more detail later on. But you can see that even though the velocity is positive, we have a negative acceleration acting on this because it's going the opposite direction. All right, and so what's going to happen to this positive velocity? It's going to get less and less and less positive, and at some point it's actually going to stop. And like everything else that you throw up, it's going to eventually start coming back down because there's an acceleration acting on it in the opposite direction. That's what this means right here. But any deceleration is still an acceleration. It just means that it's in the opposite direction that the object that is moving happens to be currently moving. So if it's moving in the negative direction, so if the velocity is negative, all right, and there's a positive acceleration applied to it, then it is going to slow down in the negative direction and then start moving in the positive direction that the acceleration is directed in. So as long as there is a difference in the direction between your velocity and your acceleration, there's going to be some sort of deceleration and possibly even changing of direction. So with that, I'm going to pause right here, and we do have a couple more slides left in this section, but I'm going to leave that for the next video. So hopefully you can follow along with that, and make sure you come see me if you have any questions. I'll see you on the next one.